Yeah, okay, let's get started. So without too much introduction, I mean, I think already people know where they are, who everybody is and what we're doing here. And I'll just give to Sam to start and roll the ball for this talk. Sam, thank you.
Okay, well, we're very happy today to have Sebastian Jaimungal from the University of Toronto presenting. Sebastian will be well known to many of us here as a significant figure in the mathematical finance community, particularly in SIAM, where he was the chair a few years ago and one of the organizers of the last in-person SIAM Activity Group meetings for financial maths and economics. Today, he's going to give us a presentation on risk-aware reinforcement learning for finance, based on joint works with many people who you can see on the slides. Sebastian, the floor is yours.
Wonderful. Thank you. Thank you very much, Sam, for the intro, and thanks everyone for taking some time out of your afternoon or evening, or maybe morning as well, to join in today. It's a pleasure to be speaking here, and as Sam mentioned, I'm going to be talking on not one single paper, but I view this more as an overview of a number of things that I've been looking at in the last few years in this particular dimension of reinforcement learning, and in particular accounting for risk in some manner. And we'll go through a number of topics related to that. It's based on a joint works with a bunch of my collaborators, and I'm going to read them out here. So there's Alvaro Cartea at Oxford, Ziteng Cheng, Anthony Coash, and Silvana Pacenti here at the University of Toronto, Yuri Saporito and Rodrigo Targino at FJV, Hariam Tatset from Barclays, and Yishang Wang at Optiver. So without further ado, I'll just give you a little agenda that I've got here. I believe it's a 45 minutes, right, is what I've got in terms of time. Great. So just, cut me off if I don't get through all of this. I rather take my time than try to rush through everything. So I'll give a little intro into the kinds of problems we're thinking about. And each of the next sections are basically 4 different papers. So there's this paper that we have on robust risk-aware reinforcement learning, where we look at a particular class of risk-averse agents and how they can robustify and how we can use RL to try to learn optimal strategies. And then we'll talk about the time consistency issue and look at some work that we developed for dealing with the time consistency issue using a class of dynamically time consistent risk measures. And it works well, but there's a small issue with it. There's a computational issue. And for that to address, we then developed a new approach based on elicitability of risk measures and extend the work. And I'll talk about how we incorporate that. And related in some way is, well, if you have a measure of risk and then you are optimizing some goal, another thing that you might want to do is, in the context of, say, portfolio allocation, is allocate money to different assets in a manner that spreads the risk in some sense equally, or you might have a particular budget that you want. This is known it's known how to do this in a one-time step setting. And what we wanted to do here is extend it to the multi-time step case and do it in a manner that is dynamically time consistent. So there's a theme throughout all of this, and hopefully you'll see the threads that connect them and get at least some of the ideas, and then go read the papers. So without further ado, here's the big overall picture idea of, well, what is reinforcement learning? I think we've all heard of it in many different settings and different contexts. I'll just give you my language for it. So I view it as simply, it's some way to solve discrete time versions, if you will, of some kind of stochastic control problem. That's the generic idea. So you have some performance criterion. Let's write it simply as a running cost. So it's the integral of some function that takes your current time, the state of some process, and the current control or action as is used in the reinforcement learning context. And it maps it to some reward or a cost. In this context, I think of it as a cost. And you aim to minimize over some set of actions. And for example, that process X could be a controlled diffusion. That's fairly typical in the classical setups that we've seen in financial math. And this leads, of course, to questions. Prototypical examples would be portfolio optimization, option hedging, stat arb, optimal switching. You can kind of write in this way as well. Of course, it's more of a stopping problem, but you can recast it. So what's the difference with RL and our classical stochastic control formulation of these is that in some sense, they want to try to learn these optimal strategies in a manner that's agnostic to the underlying model that drives the system, right? They don't want to care what's the details of that model. Here, we really specified exactly that this is the SDE, and you can go ahead and solve this using, dynamic programming principles. You go through stochastic maximum principle. You could use variational analysis, all sorts of things, but it really requires that you know that dynamics in order for you to carry things through. So the idea of RL is, well, let's try to do this in a manner that's agnostic to what the details are, and learn from this triple, if you will. It's really a four tuple, but you can think of it as a triple for now: your state, your action, and your rewards. So the ingredients are: agent observes some state of the world. These are the state variables that you wish to keep track of. For example, Bitcoin prices, you can have many different, or let's say cryptocurrency prices, could be multidimensional, of course. The agent makes some action. There's some trade that they make. And of course, that trade may affect the next price because, of course, we all know if you have excessive amount of buy orders, prices will get pushed up. But of course, there's uncertainty still there. And that action that you take and the state that you were in and the state that you get to induces some sort of reward. So for example, you could get more Bitcoin by taking this action, and maybe the Bitcoin price moves up or down, in which case you may have had a loss rather than a reward. But that's the setup. And okay, of course, environment involves a new state. So the classical formulation in reinforcement learning aims to say, sum up all of these rewards, maybe discount them, and find a way of figuring out what these optimal actions should be. When I say what these optimal actions should be, I mean, find the mapping from state to action that maximizes the sum of the expected discounted rewards. This would be the classical RL setup. Risk aware, it instead says, well, let's apply a risk measure to this variable here, y. This is this random variable. Think of it as the sum of the discounted set of rewards, or if it's a cost, sum of the discounted set of costs. And you aim to minimize this over some policy pi. So the policy pi is just a map, again, from state to actions. But we call it a policy because maybe that policy could be what's called deterministic. So for every single state, you get a unique action, or it could be a distribution over actions for every state. And there's been work where people look at, okay, take expected utility of the sum of those rewards or costs, take the variance minus the mean. We know there are issues with this, but that's a criterion that sometimes people use. There's also expected shortfall, and you can do some very naive, simple things to try to optimize this in a model agnostic manner. For example, you could parameterize your mapping from state to action using some sort of neural net. And then you say, okay, I fixed that neural net. It's a very high dimensional, high dimensional parametric family of functions. And I fixed that neural net. I run the strategy with Monte Carlo simulations, let's say, suppose you have access to that. And then you compute that criterion and then update those parameters by doing a gradient move. So you say, okay, I'm going to take that that value associated with this policy, and I'm going to improve it by moving phi in the direction of the gradient of the value. Okay, so this is a policy gradient type update rule, and you can do that very easily. And I just wanted to show a simple example. So if you did that with, say, a problem where you're hedging a call option, and all you do is you simply say, again, you map states to actions. In this context, the states would be, say, time, your current time and asset price. That's it. Those are my only two states. My action is how many units of the stock do I hold right now? So I do a very basic idea, parameterize that by a neural net, run that strategy over some simulations, get an estimate of, say, the CVAR just empirically, and then take a gradient with respect to those parameters and keep running that over and over. So on the left-hand side, you see the loss associated with this, the loss function here, which is effectively the CVAR. And then I compare it with Black-Scholes. The blue is what you get from doing this when you run this over many scenarios and you optimize. And you can see that if your goal is to protect yourself from the tail risk, the CVAR 10%, you're certainly doing better than Black-Scholes. Now, why is this asymmetric and skewed? Well, it's because the underlying model that I used here was a stochastic volatility model, a Heston model. So Black-Scholes is wrong, right? And I simply assume that the Black-Scholes hedger was using a constant volatility equal to the long run volatility of the asset. Okay, so it's a very naive comparison, but it's only to show you that you can improve upon some basic strategies by using this very naive Monte Carlo based policy gradient approach. And this is what happens if you did 20% CVAR, and if you did 30% CVAR, you start to deviate from the Black-Scholes hedge. By the way, the dotted lines here is Black-Scholes, like this, and the blue is the optimal one. Okay, so this is kind of a boring, I would say, slightly boring and but interesting in one angle exercise of running policy iteration on this CVAR criterion for hedging. What we were interested in is developing something a little more robust, but also looking at criterion that really account for how agents will, what are agents' goals in the market. So often you weigh outcomes unequally, so that's meaning using utility to value outcomes. And people often also distort probabilities of those outcomes in different ways. And so we thought of, well, what happens when an agent instead uses something like this rank-dependent expected utility from Riari's dual theory to allow them to both be gain seekers as well as loss avoiders. And so here, G is this increasing probability distortion and U is some utility functions, concave utility. Let's take the simple case. Suppose a utility is just linear utility. And then we can think of, if we take G and look at its derivative, we can think of a couple of prototypical examples. So that derivative of G, which I call gamma here, if it's 1, if it's a constant and then drops to 0, this corresponds to CVAR. So the agent is protecting themselves from left tail risk. If instead you take this gamma function to be, say, a constant, then drops to 0 and then jumps again. So now you're looking at left and right tail. And the agent in this case is weighing their left tail risk more than the right tail, but they're accounting for the potential of these profits in the right. And alternatively, they can also have a situation where they prefer to try to seek gains with some small protection of losses. And a question you can ask is, well, how does the agent behave differently in these 3 different settings? What strategies do they follow? So the formulation of the problem is looking something like this. Let's say I have a controlled process or controlled random variable x phi. And again, that phi could be a hedging strategy through time, and x phi is a terminal value of that strategy. And or it could be, say, x. Yeah, in fact, this is exactly that type of situation. And if the asset is, say, mean reverting with some sort of impact factor, that would be a nice simple example. But of course, if you have a simulation engine and then you run that simulation engine and you optimize against it, then you may be finding a strategy that's optimal with respect to this model that you've put in, this particular stochastic model for the asset price. But you know that perhaps the world is not quite that. You can't just use historical data because there's not enough, let's say. So you build a model, and this is the model that you've built, and you use that to optimize. How would you then protect yourself from the potential that your model is wrong? So that's the next question that we wish to address in this setting. And so there are many different approaches to this, and we came up with an idea that makes it amenable to this type of RL methodology in a very simple way. So the idea is as follows. In the original formulation, this non-robust version, if I have this controlled random variable x phi, well, I don't want to measure the risk of x phi directly and call that my risk. Instead, I'm going to look at a ball around x phi under my base model, and then I'm going to look at all possible distributions around that distribution of x phi, which I'll just label as some sort of x theta, that lie within a Wasserstein ball of epsilon. So this way, I know that running the strategy gives me some distribution under the model that I started with, but I know that my model may be wrong, maybe my transaction model is wrong, maybe, who knows exactly what's wrong. So I'm just going to perturb the distribution that I ultimately get and keep it, depending on the size of this epsilon, I may either incorporate more or less robustification. Of course, as epsilon goes to 0, it reduces back to this simple case. So that's what this formulation says. It says, pick an x phi, look at potential alternates that are parameterized by some parameters theta that cause x phi and x theta to be within a Wasserstein ball. And then take the particular theta that gives me the worst risk measure within that ball. And that's how I assess the risk of this potential strategy. And it's a natural way to do robustification. Another way to do robustification would be, say, don't do it on x phi, but do it on the underlying process, and then see what a strategy then ultimately gets. That's much harder to do. And this allows us also to incorporate other sources of uncertainty that you couldn't incorporate just in terms of this by modifying the underlying model. For example, if your trading costs are not the same, or if you have some uncertainty around your trading costs, you would be able to incorporate it here. It'll be much more difficult to incorporate it directly into the dynamics of S. So we developed an approach for this, and it's a policy gradient type approach using the augmented Lagrangian associated with keeping these strategies within an epsilon ball of one another. And again, the details of the formula aren't so important, but for those who've seen gradient formula before, there's some similarities. Forget about what's inside of this part here. Look at this. This looks very much like this likelihood ratio type thing that shows up, where you take the gradient of a policy divided by the policy, or the gradient of the log of the policy, and you use that to scale the performance of a strategy. So it has this similar form and flavor, but it's a bit different because of the fact that we have these rank-dependent expected utilities, and we're doing this robustification. Of course, there's also two things that you have to take gradients with respect to. There's this inner problem, so to speak, and this outer problem. The inner problem is finding the theta that is the worst risk, that has the worst risk, that is within the epsilon ball of phi, but then also varying phi. So there's an inner and outer gradient formula that we've developed for this. And there are some other subtleties with respect to how exactly do you even compute these objects. I don't want to get into the details. It's in the paper, but basically the idea is to use kernel density type estimators for it, which then allow back propagation to work. Instead, I'd like to show you some examples. So one example is, well, how do we know that this thing actually works? Well, one way is, here's a very general setup where we know what the optimal strategy was. This is an earlier paper that is a theory paper where we said, let's look for a situation where an agent gives you a benchmark, and then you know what the distribution that benchmark gives, and you want to find an alternate portfolio that improves the risk measure of that benchmark, but has the same cost. It can be cast into this problem formulation that I posed earlier. It turns out that you can solve that completely, well, analytically up to the computation of what's called an isotonic projection, and that's what we did in this paper. And then we applied the methodology of this robust risk-aware agent to this problem and compared, and we can see that, and we demonstrated that in fact it coincides. This is an example of what happens. So in this case, the X delta is that benchmark portfolio, and the X pi is that optimal portfolio that comes out of this optimization problem. And if you go ahead and actually look carefully at it, you'll see it does in fact improve on the left tail risk, and it also improves on the right tail risk. We were looking at an agent that was trying to improve their left tail risk more than their right tail risk. So one thing you see relative to this blue distribution, there's a lot of mass from here that got moved out and pushed into this point. As well, some mass in the middle got pulled out into the right tail. And these two portfolios actually cost exactly the same, but we're able to improve the risk measure. The risk measure associated with this pi portfolio is better than that of the delta. And so we solve this both using this analytical approach that I mentioned here, as well as using this RL approach, and they coincide. Another nice little prototypical example would be this example of hedging, but now something a little more interesting. So let's take a down and in call option. So it gets, there's a lower barrier. When you hit it, the option is knocked in, and it's a call when you get knocked in. The underlying model is stochastic volatility. There's transaction costs. The agent is as well loss avoiding, but also loss averse, but risk reward seeking. And the optimal hedge looks like this. So this situation here is before you get knocked in. So this is where the asset price starts above that barrier. And if you were hedging using classical approaches to hedge, you would never long the asset. But notice here, there's a sort of blue region, which means that we're longing the asset. There are regions here where you're shorting the asset, and that's what you would classically do. So why is this agent longing the asset in this in the right part of this right panel? The reason is because they are reward loving. You're looking at a situation where you're simulating under the real world measure, and you're asking yourself, how do you hedge in such a way to minimize this this left and right tail risk? Minimize this left tail risk, but seek some of this right tail risk. And the answer is, since this asset actually has some positive drift, invest in it when you are away from that barrier. As you get close to the barrier and the option is going to get knocked in, now you start switching over from basically someone who's trying to benefit from profits to someone who's really hedging the option that's about to get knocked in. And then when you're knocked in, this strategy is close to what you would normally do. It's slightly different, but close to what you would normally do. And then you can ask, well, what happens if you robustify this? This is what happens. So notice the region in which you start investing has shrunk. And that's because, well, under your base model, there's some positive return to this asset, but you know your model may be wrong. So when you start to take advantage of this positive drift of the asset, you become more conservative when you robustify. And so it does exactly the kind of things that you would expect an agent to do, which is quite nice, quite promising. And with that, I'm going to switch over into the next chapter, which is this time consistency. So a big issue with both of the things that I mentioned here is that if you are going to make multiple decisions and you have sort of intertemporal view of what you're doing, you will run into potentially time consistency issues. So rather than go through this classical, well, I'm going to put this classical example and quickly point out what the time consistency issue is. So imagine that you have this in front of you. You're sitting at time 0, and you have decision points here and at time 1, which means that you have decision points whenever you get to these 3 nodes. The splits that happen between these decision points are not something you can control. So the universe is either going to throw, if you say, take this up decision, then the universe is either going to throw that to you or that. And similarly, if I take this down decision, the universe will throw that to that. And you can make decisions at all of those red points. So if you ask yourself, look at this problem, the terminal random variable is y, pi is your policy, which means what do I do when I'm in any one of these nodes? And you say, what is the thing that minimizes CVAR? Well, the optimal decision is what I just drew there. You go up first, and then no matter what happens, go down. And then you say, okay, let's do that. Let's go up. The universe throws this down scenario at you. So you now have ended up in this S1 up prime, this red node. And then you say, well, what's optimal? I want to minimize CVAR of the random variable one step ahead. Well, what's optimal is actually to go up. That's inconsistent with the decision with your policy, which was a state-dependent and time-dependent policy, but it's inconsistent with what to do once you get to that state that you get to when you made what you thought was optimal back here. So this is the issue with time consistency. So there are many approaches to address this. I'm not going to go through the whole literature review. There's a really nice unified approach to this by Tom and Igor and Pietra, as well as numerous other people. We're going to focus on the way of resolving it using these nested conditional risk measures. So, and for that purpose, we need to get our heads wrapped around a little bit of what do we mean by dynamic risk measure. So dynamic risk measure is simply a mapping from a sequence of costs that are measurable at those future times, say t to t plus 1, t plus 2 up to capital T, into something that's measurable at time t. And you have a whole sequence of those for all possible combinations of little t and t. So the time consistency issue is as follows. This is the formal definition of strong time consistency. It's better with a diagram. So what's the diagram? The idea. Suppose I had two sequences of costs, Z and W. And over these first portion of time, these two sequences of costs are equal to each other almost surely. Okay, so they're random variables and they're measurable at the appropriate time, but they're equal almost surely at each point. So ZT1 equals WT1, ZT1 plus 1 equals WT1 plus 1, etc. I guess I didn't need the subscript plus 1 there. That's okay. So they're equal almost surely. And then let's say I now have the remainder of those two sequences of costs, and they're not equal to each other almost surely. So over this first portion, they're equal almost sure. The remaining portion, they're not. But you use some dynamic risk measure, which maps that future sequence to an FT2 measurable random variable. So there's some number there. And I prefer, let's suppose that I actually prefer this the top sequence to the bottom sequence. Well, if I prefer the top sequence to the bottom sequence for this latter part, and they're equal almost sure over the first part, then I should prefer, whoops, there we go. Then I should prefer the risk of the whole sequence for the top to the bottom. Whoops. So I should still prefer, I don't know why it keeps doing that, the top to the bottom. So again, the idea is they're equal on this highlighted yellow part. I prefer the light blue on the top to the dark blue on the bottom. Therefore, I should prefer the whole sequence on the top to the whole sequence on the bottom. So this induces it's a particular type of time consistency, but it seems somehow natural and palatable. So what a nice result from Ruchinsky says that if I have a couple of extra properties, so let's read them out. They're really simple. If I take a risk of a full sequence and this is FT measurable, it basically comes out. That's a translation invariant property, but an FT measurable one. Okay, the risk of 0 is 0. If I have an event that's FT measurable and I scale all future costs by that FT measurable random variable, it comes out. This is a type of homogeneity. Okay, so if we have these extra three properties, then any dynamically time consistent risk measure has this beautiful recursive representation. So I compute the risk of the last cost, and then I add that to the cost I have at that time t minus 1, compute the risk of it, and then I add it, and so on and so forth. I have this onion, this layering. I start at the end, compute the risk, add the new cost, compute the risk, add the new cost, compute the risk, add the new cost, and you recursively go back. So there's sort of an if and only if statement there that if I have those properties and we want a strong time consistency, then there must exist a risk measure of that type, and every risk measure, every one-step conditional risk measure of that type will induce one. So this is really nice because it naturally leads to an idea of a dynamic programming principle. In particular, if I define this so-called risk to go, if I'm at some future point in time and I only look at all of the remaining risks and I compute the risk measure of it, that risk to go satisfies this type of recursion. It's a nonlinear form of recursion. If the conditional risk measure is simply a conditional expectation, then this boils down to expectation of the sum of the costs. Otherwise, it's some nonlinear distortion as you go through time. So this is the result, one of the key results as well in this Rutchinsky paper. Together with Zitang, my postdoc here, we extended this to the case when you have actually latent costs and state-dependent risk measures, and your actions can be random. Also, Igor and Tom and Andres Rutchinsky as well, they develop a Bayesian approach to slightly different variations of model uncertainty with unobserved costs, using this new notion that they've introduced, as so-called risk filters. And so you can take a look at these two nice extensions. For the rest of this paper, we're going to stick to the simple setup here. So a natural question is, if I have now these variables, these costs, parameterized by some strategy, or actually I can just write it here. So there's some strategy for my Zs, a policy, and that modulates my future costs, such as a dynamic delta hedging strategy, some dynamic hedging strategy. How do I optimize this risk measure? That's a question that we addressed in the first paper with Anthony Kalash. And one way, again, to do it is by using a sort of a policy gradient actor critic approach, where you approximate these risks to go by some sort of neural net that maps you from your current states into the value. And at the same time, you have another network that parameterizes the policy. What is the delta? What is the hedging strategy that you use, for example? In order to make this methodology work, you need to have some gradient update rules as well. And so we worked out what those are for a particular class of one-step conditional risk measures, in particular convex risk measures. And why convex risk measures? Well, because they have a very nice representation using this dual representation where you write the risk measure as the supremum of the expectation over alternate measures plus a penalty for those alternate measures, where that supremum is taken over measures that are inside of a particular risk envelope. So if you use this representation, it turns out that you can write down a very nice recursive representation for the gradients of those value functions. And you can do more. You can say that, well, since we're parameterizing things with neural nets, can we arbitrarily accurately recover the true value function? And it turns out, yes, you can. Here is a small example showing the result of some of this. So here, let's focus on the ones that are labeled just CVAR. So this, and this. So these are convex risk, one-step convex risk measures, conditional risk measures. And what we've done is taken an underlying model where there's stochastic volatility, there are transaction costs. You don't observe volatility like people often assume. We would just throw it away, say that's not part of our state variable. And then we said, let's find the optimal strategy that minimizes, say, CVAR of 0.1. This gives you some strategy. And then the question we asked is, what price would an agent charge for the option if they're to be made indifferent from to doing this hedging strategy? And how are they made indifferent? Well, we're ensuring that the dynamic CVAR at level 0.1 is 0.2. So that means that they charge the agent $0.2. And if they charge $0.2, then we know what their optimal strategy would be like. And then we can look at the distribution of that optimal strategy by charging them these $0.2. And in the case of CVAR 0.1, their P&L would be this purple one that you see here. And because this agent is risk averse, quite risk averse, they're charging a high price, which is why the whole distribution is shifted over to the right. And in the left panel, this is a scatter plot of their terminal P&L before they pay the agent what they owe them from selling that option. And you can see the purple scatter plot is, for the most part, lying above everything else, again, because they're charging a high price, because they are very risk averse. As we increase the level of confidence, then they become less and less risk averse, and each one of those P&Ls goes down. So that's the purple, then this sort of this purple, then this blue. So it moves in the correct direction. The agent charges less when they become less risk averse. So the distributions move over. In all cases, though, the dynamic risk measure associated with their particular criterion is always 0.2. So they're always indifferent to doing this, however, they're following different strategies. The ones with the penalty, this is when we incorporate this entropic penalty with CVAR simultaneously. And given time, if you want to ask about it, we can talk about it at the end, because I want to move on. So although we can do this, I mentioned that there's a problem here. There's a problem because if I'm sitting at a point in time and I wish to estimate the remaining risk to go, I need to do a nested simulation for every single time, for every single state that I'm in order to estimate that well. So there's a computational bottleneck here. So even though there was no methodology out there before for being able to do this, there's some related work by Tamar, but it wasn't as comprehensive, nor was there a proof of the accuracy. This methodology runs into potentially a bottleneck in computational issues if we get to very high dimensions, and we have to do many, a lot of nested simulations to estimate the running risk to go. So we then started looking at the notion of elicitability and using elicitability, the elicitable maps, to elicit these risk measures. So very briefly, the idea behind the elicitable map is that if I have some statistical measure that I want to estimate, if I can find a score function such that the expected score on the samples, when I minimize a certain argument of that score, I extract that particular object that I'm after. For example, for mean, it's very easy. It's just take the expectation of a minus y squared. If I minimize this over a, then a is the mean of y. And this holds true even when you want the conditional version of this expectation. So if I want to estimate the expected value of y given x, some other random variable, if I minimize this over all functions g, then I will elicit the conditional expectation of y given x. The function g that does that will minimize it. And there are generalizations of this to the context of risk measures, of a certain class of risk measures, in particular spectral risk measures. So we utilize that structure and define sort of a class of one-step risk measures that we are able to elicit. And once again, we prove that if you do this, in fact, your running risk to go is in fact within or there exists always, right? With any theorem of this type, it's the existence of, not the construction of, right? There exists neural nets that will do this. So we know at least doing the methodology will be sensible. And in this context, what we need to do is we need to build this sort of actor-critic type methodology together with policy gradients. So the actor here would be the policy, the hedge strategy, if you will, that you're using. If it's a portfolio optimization, then maybe you also want to be looking at your wealth and your percentage of investment in each asset. To elicit, once you have that, you need to develop these critics, which are the risk to go. The risk to go, for example, if you were minimizing, say, the CVAR plus mean, that's a way of trying to seek some rewards but protect yourself from tail risk. Then you need to elicit the mean, you need to elicit the value at risk, as well as a CVAR, because their CVAR by itself is not elicitable on its own. It is jointly elicitable. And this goes into your performance criterion. And again, you can compute, we derive some gradient formulas that allow you to do this. And you can repeat some of the previous work and you'll get a bit more efficiency in both memory as well as in speed. So some of those ideas, we then realized, in fact, there's a really nice application into the setting of dynamic risk budgeting. And I believe I have 5 more minutes, yes? Okay, cool. I think I'm going to get there.
5 to 10.
Mm-hmm. Okay, good. Then I'll keep the pace as is. So what's dynamic risk budgeting? Well, in risk budgeting, just in the single time period setting, the idea goes back to Mallard. And the idea is that if I have a universe of assets, so let's say they're X1 up to XD, these are the value of those assets in one time step. And I want to allocate the percentage, I want to allocate my wealth to each one of those assets, but I want to ensure that the wealth and the amount of risk that asset 1 has is the same as the amount of risk that asset 2 has, is the same as the amount of risk that asset 3 has. So I want to allocate my risk equally across. Or alternatively, I want to put most of my risk in one of those assets and then spread it equally along others. In general, there's some allocation, B1 up to BD, that I want to spread my risk across those assets. So this is a problem formulation that people have come up with in a single time period. And it turns out you can do a lot of cool things in the one step. But of course, it depends on how you measure the risk of that portfolio. And what does it mean for an asset to contribute a certain amount to the risk? In the one period setting, if you use homogeneous risk measures, so that is the risk of lambda times x is equal to lambda times the risk of x, then you can apply a simple Euler theorem, and it tells you that the allocation, the risk contribution, if you measure it as the partial derivative of the position that you hold in an asset of the risk times the position you hold, then these will sum up to the total risk. So in one period, it's quite known how to do it. But how do you do this in the multi-period setting in a manner that's time consistent and in a manner that your decisions will be state dependent, but they don't change as I illustrated earlier when you get to states in the future? So this is our working paper, so hot off the press stuff. Now we have pressure to put it out there because we're talking about it. So the idea is we're going to focus on a subclass of one-step conditional risk measures. We're going to use dynamic risk measures, as we discussed earlier, as the way to measure the risk of a sequence of costs. And what are these one-step risk measures we focus on? These are the so-called distortion class. One way of writing it is the risk of this random variable z is the expected value of z times some distortion function. Think of this again as those sort of alpha beta type risk measures I introduced before. There's 0 and then 0 and 1. If it's only a constant and then drop to 0, that would be CVAR. Okay, so CVAR would look like this. It would be constant, drops to 0. So that's what this gamma is. We actually developed the setting where this gamma could, in fact, depend stochastically on time. So this level, for example, could depend stochastically in time. For example, maybe at time 0, you have a risk. You want your CVAR level to be the 10% CVAR level, but if your wealth drops below a critical level, you want to be really risk seeking, and you swap to all of a sudden become a risk seeker. Right. So in principle, this works in our setting. So these are the class of distortion risk measures. F here of Z is the CDF of Z itself, conditional on the information you have. So it's a conditional CDF. So you define the risk to go now slightly differently than we did earlier. So earlier we had just a random variable Z plus the risk of the remaining portion going forward, the V T plus 1. Here we have this scaling factor that happens. And the reason that we have this scaling factor is to ensure that we have a way of enforcing the self-financing condition on a strategy. It's a subtle thing that shows up in this setting that actually took us quite a while to finally hone in and pin down. So this is a weight factor that's a stochastic weight factor that's not there in the classical setup of the dynamic risk measures. So with this recursive definition of a risk to go, then there's several key results. So one is, first, we define a risk contribution as a Gatto derivative of this risk to go in the variable corresponding to the position in that asset at that point in time. And if that's not familiar to you, that's okay. You can ask on a horribly misspelled Gatto there. There's like an extra U and X. So you could ask during the Q&A period, why is this an interesting object to define? Well, it turns out that indeed, if you sum up these objects across assets, then they sum up exactly to the risk to go. And again, this follows from an Euler-like theorem, but on the space of random variables, effectively. Next, we can actually compute explicitly what that risk contribution is in terms of, I mean, that's the formula. Don't bother to digest it. This is just stating you can, in fact, compute it. There's a really weird object that shows up, and that's this uniform random variable that's co-monotonic to the remaining risk to go. And it's something that that caused also a lot of headaches in implementation, but we figured it out finally. And so now at this point, we've been able to define how do we measure the risk of this portfolio. We now have a way of defining a risk contribution, which adds up to the risk. What's a dynamic risk budgeting strategy? A dynamic risk budgeting strategy is a natural thing. You want the risk contributions to be proportional to the risk to go. That's it. Okay, so great. So how do you now attain that? It's not obvious. How do you find portfolios that attain this? Well, it turns out we've been able to construct a sequence of recursive of optimization problems that lead that when you optimize them and rescale them appropriately, you in fact get a self-financing strategy that is a risk budget strategy that does have the correct dynamic risk budgeting. Okay. So that's the theory part of it. And then there's the question of, well, how the heck do you go about doing that? Well, this arg minimization, if you look at it carefully, it is basically of the form that we discussed earlier. It's of the form of this minimizing some sort of dynamic risk measure. There's this extra expectation operator that sits out front, but that's okay. We can deal with that. There's this extra term, which again is also slightly different, but this you can deal with. So we've been able to, again, go through the procedure and implement it utilizing the methodologies of these elicitable maps, and it works. So this shows you, this is a fairly simple setup. It's 3 periods, two risky assets, but it shows you this thing converges really quickly. In fact, after just a couple thousand iterations, the sum of the risk contributions add up exactly to what they should. It should sum up to 1. The risks to go all converge to the same thing, even though they start quite differently. The risk contributions themselves also are exactly what they should be. And I think with that, my time is up. So I'm just going to say, thanks for the attention. And I hope I've at least intrigued you to go check out these different collection of works that really pull together ideas of risk and dynamic risk measures, all into the context of RL and with lots of potential for various financial applications. So thanks a lot.
Thank you, Seb. We've got time for a few questions. I know there was one from Agostino. You want to come in, Agostino?
Yeah, that was that is related to the very first part of the talk. So I hope you still remember. I think it is related to you showed the figure where you compare the price of a call option using a stochastic volatility model under Black-Scholes and under the reinforcement learning approach, and then you have shown that in this case
the hedging case, yeah, just the basic, the very first one.
Yeah, the very first, exactly. No, I was yeah, exactly. I was wondering if you do the opposite. Suppose that you price the option using Aston, so then the model will be correct, and then you can see how well would the reinforcement learning approach do. So,
how well will recover the Heston?
Yeah, exactly.
Hedge? Yeah. Well, but there's a question though: do you feed it the volatility or not? Because if in the Heston, if I know, how do I calculate my hedge? Well, I have to know the instantaneous volatility, right? In the classical way of doing it.
Yeah.
So if you do that, it should, in principle, it should, right?
It should recover, it should coincide exactly with
when,
you, right?
Well, that's when, but of course, since you're hedging in discrete time, you're not going to get exactly the same. Right?
Apart from the fact that if you make the interval smaller and smaller, the discrete grid, then you should get closer and closer, right?
Yeah, if you're simulating both under the real world and risk, if your real world is the same as the risk neutral, right? Because it's an incomplete market as well.
Indeed. Okay.
On this, I was wondering why you chose to exclude the volatility, given that means that your system is no longer Markov. So the state variable you get is not a good state variable for a control problem.
Yeah, that's right.
So
We wanted
why
to
did
hurt
you
it.
choose to do it this way?
Yeah, we just wanted to hurt it. we wanted to put the RL agent in a handicap to say, well, you don't observe this volatility. All you observe is price. Can you infer anything from the from the history of the prices, the price process, to induce something about the volatility?
Thanks. Becca.
Hi, can you hear me?
Yes, we can.
Yes.
Okay. So my question is so in the very beginning, when you show when you formulate this robust scheme for reinforcement learning, what if you consider, instead of considering the agent against the nature, as it were, what if you consider the problem of nature? So if you interchange the inf and the sup, will all this still go through with minimal change or no?
I don't have an immediate answer for you. Yeah, if you interchange the inf and the sup, yeah, I don't have an immediate answer. But it's an intriguing thing to think about.
I see. So my second question is why maybe this is stupid, because who doesn't love Wasserstein? But why did you choose Wasserstein?
It's for the reason you just gave. Who doesn't love Wasserstein? No, well, I mean, the reason is in this setting, because we can easily compute the Wasserstein distance between any sort of simulated set of x phi, the thing that the agent controls, and alternates, right? We can compute that distance pretty straightforwardly, because it's one-dimensional, and there's a nice analytical tractability there. But yeah, we could do something else. KL wouldn't work so well, because again, you have discrete points, right? So it's more natural in some way to use Wasserstein distance in this case when you have samples.
A related question was asked in the Q&A by someone anonymous. How do you determine epsilon, the radius of the Wasserstein ball?
Yeah, that's always a good burning question. So one answer which we give actually in this paper here is, suppose you're willing to admit that you're willing to accept a certain amount of deviation around your standard deviation. So meaning, if I take a strategy, I get some distribution, and let's say the standard deviation is, I don't know, 1, okay? And you want to consider alternate distributions that are, say, well, the standard deviation isn't going to be 1, but somewhere between, I don't know, 1.1 and 0.9. You can translate that into an epsilon. There's a way to reverse engineer it this way. So in other words, how much uncertainty in your volatility are you willing to accept? You can translate it somehow into an epsilon. That's one way that potentially you can do it. I know that there are these bounds on, for example, how large should you choose epsilon such that the probability that the true distribution lies within that epsilon is above some threshold. There are bounds like this, but they're kind of vacuous. They're too large. So I think this kind of idea where you say, okay, I'm willing to add in this amount of extra uncertainty into my distribution from my base model, and inverting that to give you an epsilon is a little bit more natural. Or alternatively, you just do it with different levels of epsilon and then decide on what do you as an agent feel most comfortable with.
Mehrdad, would you like to ask your question?
Yeah, thank you. I wanted to ask about the nested risk measures, the setting of Richinski. Do you think that this setting would lead to over conservative policies because it calculates the risk in these multiple time steps?
Well, I think that all depends on what your choice of the one-step conditional risk measures are. If they're overly conservative, then the whole thing will be. And it's not obvious. For example, if I said, let's take the sum of the z's and compute, say, CVAR at level 0.1, how does that differ from doing the one-step conditional risk measures at level 0.1? And the answer is, those are fairly different. But the point is, you shouldn't use the same level of CVAR for the one-step conditional risk measures that you would for the risk measure on the whole sum. You should tune it differently. So if you tune that one-step conditional risk measure differently, you'll get something that's of the same order of magnitude. And that's one way that you can do it, right? You can say, fix a strategy, look at the cost, compute CVAR at level 0.1, and then say the sum of the costs CVAR at level 0.1. Let's say that turns out to be, I don't know, 1. Now find the level of CVAR such that the dynamic CVAR gives you the same level of risk. You could do something like that. I'm not sure if that's a reasonable thing to do, but it's something you could do. So would it lead to more conservative results? I think it all depends, again, on what you've chosen for those level of one-step conditional CVARs. And as you seen here, that level of CVAR does play a role, obviously, in what your optimal strategies look like. And it's up to you as an agent to then, get acquainted with what different levels of CVAR are for your problem, right? Because it's not obvious a priori.
But I guess that there's not a direct connection between that. If you want for example, the 0.1 confidence level for in an example for in a year, then we don't know what confidence level we should choose for each time step that we use. There's not a direct way to calculate this one-step confidence levels.
Well, I guess you have to ask yourself, what is it that you want to achieve, right? There's no easy map from knowing the CVAR level over the sum of the things over the whole year versus the conditional ones. That will, it's it'll give you some number, whatever you put in there. But the question is, what are your goals, right? What is it that you're aiming to optimize over?
Thank you.
So I think it's non-trivial.
There was another anonymous question. Your last optimization problem, is it convex, or are there conditions where it is convex?
Yeah, very good question. I like this question. Sorry, those were extra slides. This one?
I guess so.
It is strictly convex for every T. And so we know that there in fact exists a optimizer. This is indeed the case. That's when you search over all FT measurable random variables. Now, of course, when we parameterize those with neural nets, now we've lost it, right? So in theory, we know that there exists a unique optimizer to this, to these problems. But when we implement with neural nets, then we have to not throw up our hands, but we just say, well, let's do it and see what we get, right? But this is always the case whenever you're doing something, taking a convex optimization problem and then parameterizing them with neural nets, you lose this. Hope that answers it.
Yifan, would you like to ask your question?
Yes. Hi, Professor. So our question about that Weierstein ball.
The Weierstein ball. Okay. Yep.
Yeah. So my question is about how the setup of the Weierstein ball is related to the parameter uncertainty in the underlying process.
How is it related to the parameters in the underlying process?
The parameter uncertainty. Yeah.
The answer is a priori, it's not.
Mm-hmm.
Right? A priori, it's just the underlying process in this setting. We're not assuming anything particular about it, right? You could use whatever process you wish. The epsilon, in some sense, is allowing you to say, well, let's say that your underlying process is a CIR process, okay? And there's some parameters there. Well, maybe it's not CIR, maybe it's actually Ornstein-Uhlenbeck, Maybe it's, you know, an exponential of an OU, something like this. It's completely different, right? They're unrelated processes that could potentially be driving things. But nonetheless, all of those alternates lead to some distortion of your distribution. Now, they shouldn't lead to just completely wild and completely unrelated to what your reference model is. So that's why you pick an epsilon. But there's no mapping necessarily from the model that is within this ball to something within the parametric class of model that you've chosen, right? Not necessarily.
Yeah.
There will be some models in that class that are within this epsilon ball, but not all models within this epsilon ball are in that class.
Yeah. It's kind of like a non-parametric view of the model setup.
Yeah, that's right.
Yeah.
Yes.
Yeah. Okay. Yeah. Thank you.